It's great to be here back in the US, especially with the geography students, and of course, especially with my girlfriend Nadia, who's in the back, and the speakers talking about my startup GreenEye, Coffee's geospatial analytics group. So I guess I'll talk first a little bit about the history of GreenEye, its inception, the idea behind GreenEye. So I was working in London at a fintech company after I graduated from McGill. I don't know if any of you have been to London, but it's a very cold, depressing city. And I was always interested more in kind of geospatial analytics and not so much fintech, and still, interested in the startup scene in London. But so I left my job in London and I went to India with very little plans, other than to try and look at how I can better implement my skill set coming from a background in geography with remote sensing, satellite imagery analytics, specifically in tropical agriculture in India. I kind of visited a lot of coffee farms, and so this is how I eventually came up with the idea, or led to the inspiration of monitoring coffee yields based on how much coffee is drying in the sun. So I don't know how many of you have ever been to a coffee farm, but coffee is a commodity, which to begin with is an extremely important commodity on the financial markets, second only to oil and gas in terms of volumes of trade. But coffee is also very unique, unlike other commodities like corn or soy, which are grown in full sun. And so with satellite imagery, you can just look directly at those crops and run something like a NDVI, for example, Normalized Differential Vegetation Index, which essentially tells you the chlorophyll levels of the plants, which is then obviously a good indicator of the health and the harvest. But coffee is a bit different, especially Arabica, and in India, in most countries, coffee is grown in the shade. So you have a very thick canopy layer that is obscuring the coffee plants themselves from direct sunlight. So obviously, satellite imagery is not penetrating the trees. But coffee is laid out into the sun in these big concrete basins with a very even consistency. And so by measuring the fullness of these basins and with a factor, you can derive what the harvest is for every coffee farm. And then I'll actually just take you right to my website, greeneye.co. And then when you graph kind of what is the harvest as in terms of the percent, how full are these drying basins with enough sample size, I derive national statistics. So with about 200 different coffee farms or drying basins that I'm monitoring in Brazil, and just by looking at monthly averages and then deriving the area under the curve, then Brazil's harvest, based on my statistics, is down 22.28%, which is in line actually with market knowledge, because actually 2018 was an amazing year for the Brazilian coffee harvest. I don't know how many of you were following the 2018 Brazilian coffee harvest. It's actually led to an incredible decrease in coffee prices, and there's a kind of coffee price crisis all around the world because the 2018 harvest was so good. But luckily, Brazil's not producing as much coffee as they did last year. So this is kind of my current product in GreenEye is monitoring coffee harvest in Brazil and a few countries in Central America. Any questions up to this point?
Yeah. Who's the biggest coffee producer in the world?
Brazil. They produce over 50%. Second is actually Vietnam, and they just started growing coffee in the early 1990s, and they're already number 2, which is incredible because they've come from nothing. Pretty powerful in coffee markets. There's a lot of growth actually in Southeast Asia. Myanmar is growing coffee, northern Thailand, even southern China near the border with Vietnam is growing a lot of coffee. So it's an expanding market, and also coffee demand, luckily, is increasing about 2% every year, actually. A lot of more kind of people are drinking coffee in places like India and China.
Is there a correlation with how fertile the ground is? With how much coffee is grown in a place?
And with what?
Like say Brazil is the leader in coffee production, right? Is Brazil's grounds more fertile than say Vietnam's? Is that why they're producing more? Or are there other factors?
Yeah, it's actually really the kind of geography layout. In Brazil and Vietnam, the coffee is grown in very flat lands, so they use big mechanical harvest pickers that kind of shape the berries. Whereas like pretty much everywhere else except for Brazil and Vietnam, all of the beans are picked by hand because they're on sloping hills with it's much more difficult to run the machines.
Thank you.
Yeah. Yeah. So this is currently me and my partner. He's doing some of the computer stuff. Yeah, we talked about this, the canopy layer. My method is all quantitative, whereas a lot of the commodity markets look at coffee in terms of qualitative. How many, how wet is the soil, or like what is the flowering, is, I also do individual site monitoring for large coffee farms. So yeah, a lot of interest in this data, but still there is actually a lot of competition because you have some big commodity traders, like here in Singapore we have All, which is actually a huge world player in tropical commodities. But they spend so much money, like millions of dollars going out into the field, checking how moist the soil is, checking to see the flowering conditions, and so this is all actually before the actual harvest. So what I found with my method is a little bit retrospective in terms of what the competition knows, but there's still a lot of implementations for it in terms of verifying how much coffee an individual farm harvests. A lot of problems with coffee theft actually in places like Brazil. Yeah, so anyways, let's just get right into Google Earth Engine now, because I think that's enough about GreenEye. So has anybody worked with Google Earth Engine in the past? ArcGIS? JavaScript? Anyone here?
JavaScript,
Yeah.
yeah.
Python?
Yeah. Yeah.
SQL?
SQL.
SQL?
SQL, yeah.
How about C++?
Yes,
Yes.
definitely.
HTML?
Yep.
Yeah.
Tough crowd. Yeah, so Google Earth Engine is a planetary scale platform for Earth science data and analysis. What's really incredible is the amount of data. It's all publicly available data. Most of it's coming from the US or NASA with Landsat, or the European Space Agency with Sentinel-2. Those are really the two leaders in terms of acquiring free, publicly available satellite imagery or LiDAR. India has been launching a lot of satellites, most of them going up recently, and but their coverage is actually mostly over India. But yeah, so here is kind of a little catalog of the data. So the surface temperature, climate, atmospheric, weather, and then obviously the imagery, Landsat and Sentinel-2, and Sentinel-1, and probably some of the other Sentinels too. But these are really the main ones that I use. Landsat has about a 30-meter squared resolution, whereas Sentinel-2 has about a 10-meter squared resolution, and they're multi-spectral. So does anyone know what multi-spectral imagery is? I'm sure you've obviously read it. Anyone want to try and define multi-spectral imagery for the audience?
Different spectrums of the electromagnetic wave.
Yeah.
Like infrared or
Exactly.
different kinds.
Yeah.
It's
So
fine.
yeah. Someone once said that humans aren't perfect, and it's true that humans can only see really the primary colors and then a mixture of green, blue. Whereas if you move on beyond red, then there's near infrared, and then beyond near infrared, there's short wave infrared. So near infrared we talked about with NDVI. Plant leaves, the chlorophyll inside of them reflects certain amounts of near infrared, so more chlorophyll means more near infrared being reflected back to the satellites, and that's how NDVI works, is by calculating the index of near infrared versus the red as kind of a reference point. And there's also WDI, normalized water differential index. And that works with, instead of near infrared, that's shortwave infrared, and shortwave infrared reflects amounts of water. So when I'm looking at coffee in drying basins, I'm mostly using near infrared, because you're looking at the beam as a vegetative matter. But I'm also running some experiments where I'm looking at shortwave infrared and WDI to see actually how far in the drying process the coffee beans are. Because they take about a week to dry. And then based on the NWBI, you can see, were these beans freshly laid out, or have they been drying for a week and they're already ready to kind of rake up. Landsat and Senegal both have a temporal frequency of about 14 days. It's generally better at the equatorial regions, which is again a plus for coffee. And the fact that coffee takes about a week to dry. Anyways, we should stop talking about coffee and talk more about Google Earth Engine. So there's high resolution imagery, MODIS, terrain. So terrain you can use, if you're looking to calculate things like watersheds or slope, what north or south facing slope for ideal agricultural growing conditions, land cover, although that's not global. So there's really a lot of data out there available. So let me show you kind of this is the Google Earth Engine interface. So anyone who's actually interested in getting set up with Google Earth Engine, it's kind of by invite, so you have to request access. I'm sure if you have an address email, you'll probably accept. So this is the basic interface, and you call your data sets, in the first line. So here I'm looking at Landsat 8, so I call in here are all of the data sets. Satellite 5. I'll show you, so this is a very basic NDVI mapper that I'm using Sentinel 2 imagery. So you have your start date and your end date, which just has to wrap around one day that has satellite imagery. And,
is this better?
yeah, that's better. This is a region of interest that I put over botanical gardens here in Singapore. Then you can add layers by specifying which bands. So here you have band 4, which is red, band 3, band 2. So it's red, green, blue. So this is and then here's calculating NDVI with Landsat 8. So here I've defined a region of interest just with this polygon, and then by setting your dates, I've written this code just to graph NDVI over time. Which one of the biggest problems in satellite imagery is cloud coverage. So obviously clouds don't have high NDVI, so they're pretty hard to filter for as well. So a lot of the time when I'm looking at the imagery, I have to go through day by day and sort and take out the images that actually have cloud cover. What I was thinking we could do is go through one of the tutorials in Google Earth Engine. This one is for calculating forest change cover. Any questions up until this point?
Actually, I was just wondering, like, why is it better to use like NDVI rather than just using like colored image?
Or specifically for my use case with coffee, because the color of the coffee often looks exactly like the color of the cement when it's drying, like very like light green or cementy kind of gray.
Oh.
So you actually can't see it with the visual light. So,
Okay.
and so by using UV or infrared and NDVI, you know you can very clearly see the pixels that are vegetative matter versus those that are just concrete empty.
Right. So like the NDVI, using NDVI, you can only read the light reflected from coffee beans, not cement anymore.
Well, the cement will have a negative or a zero NDVI value. So NDVI runs from a scale of -1. So like a body of water would have -1 because there's no vegetative matter on it. And whereas like the most green forest that you can imagine would have a 1 because it's the highest of the vegetative scenarios.
I have a small question.
Mm-hmm.
There are infrared cameras to detect even with blocked surfaces. Like if I have some heated body and then a blocked surface and a camera over here, that can kind of detect this. So is there any like can that still happen with satellite imagery with NDVI in like a cemented area, but you have coffee beans in that building or something? Can you still do that?
And use the camera to
The satellite imagery to actually capture the coffee. This is a strange question because you wouldn't need to do that, but I was just wondering if you can.
Wait, sorry, can you repeat the question again?
Oh, okay. So like, if you have some blockage due to like I don't know, any cemented structure or anything like that, and can your satellite imagery still be able to capture NDVI data or near infrared data like from plants or coffee?
No.
You can't?
So yes, cloud cover is a big problem, and also a lot of countries, like Colombia, for example, they harvest during the rainy season, and so they dry the coffee in greenhouses, and so there's a case where you can't use this method because the satellite imagery doesn't penetrate through the roof of the greenhouse or the clouds. Yep.
How do you know that it's coffee and not some other crop?
A lot of background research and a lot of field work as well, going in like manually defining the coordinates where these drying basins are in the coffee farms and the coffee growing regions. Yeah, so it's a very labor-intensive process of actually knowing where the coffee is drying in the sun.
So you actually have to go down to Brazil itself and
yeah, I've been in Brazil, walking around looking for drying coffee. And also there's some databases that I managed to get a hold of coffee farms around the world, things like this. So yeah, building the reference database is pretty intensive. Any other questions from the geographers? Or?
How do you correct for cloud cover?
Yeah, a lot of the time, if there's cloud cover, I just throw that out, and if you have enough sample sizes, if your sample size is large enough, then it doesn't really affect the data, I don't think.
So your process able to predict coffee yields, or is just able to measure on the spot?
Measure on the spot, yeah. Okay, so not predict coffee yields, which is a lot of the competition is much better at doing the prediction. There's commodity traders or coffee researchers that are down on the ground looking at the weather and the climate data. Like temperature, for example, is a huge factor in coffee because frost kills coffee like instantly. So if there's ever a frost in Brazil, that coffee production is going to go down significantly. Is there any other questions?
Yeah. You just now mentioned that removing the data from cloud coverage, like the ones with cloud coverage, is actually a labor-intensive process. Like, why does it have to be a labor-intensive? Like, I'm pretty sure it's labor-intensive because you must have tried something and then that's why you have to manually do it. But
well, there's so many different types of clouds, and they all have very different reflective values. So the spectral signature This is important, I should actually show you. So here I have the inspector tool up, and those are these, have these layers. So yeah, this red polygons over the botanical gardens. So here we see botanical gardens area. So here you have a forest, some residential. And so here is what you call the spectral signature. So band 1, that's actually, I forget what band 1 is, but band 2, 3, and 4 are the 3 primary colors. Red, green, blue. Well, band 4 is red, and then 5 is near infrared. Band 6, near infrared again, and then you work your way. Band 8 is shortwave infrared. And these other bands are kind of different variables, not actually on the spectrum. So you pretty much build your spectral signature between bands 2 and 8. And yeah. And then 10, so all the way to 12. So you have, so these are all of your different bands. And they actually also have different spatial resolution. So if you're doing something that is, trying to classify an image with the bands, you want to use the ones that have the better spatial resolution. So obviously the blue, green, red, and the near infrared band 8, which has, again, a spatial resolution of 10. And so the spectral looks something like this, where you have every sort of item, everything that you detect is going to have a unique signature based on light it reflects within those ranges. So green vegetation, let's match this with, let's see. So here's visible light, near infrared, and mid-infrared. So green vegetation has higher reflectance values in near infrared than soil, for example, on this chart. That's obvious because green vegetation is reflecting more near infrared light from the chlorophyll within the plant, whereas water doesn't reflect any near infrared, and that's why water will have NDVI value of -1. So everything is going to have its own unique spectrum like this. Coffee, cement, roads, water, cars. And so this is an example of what would be hyperspectral signature, because you have, what's a graph? So you have everything defined along every point. Whereas multispectral, if we look back at the inspector here, you don't have, it's a bar chart, so you only have one value for band 4. And you're limited to maybe about 10 different data points from which you can build your spectral signature off of. So look at the spectral signature when I click here on the cloud. So let's see, band 8 is near infrared, so that's 4,000. And then on the vegetation, 2,800. So they have, it's not just that value, all of the values have, you can see the different signature. And because the cloud is, clouds are, different clouds have different spectral signatures, so that gets back to the question of why you have to filter clouds individually. Yeah, so I wanted to go through quickly. There's some really good tutorials on Google Earth Engine. Also, the Reddit page on Earth Engine is a really good resource. And YouTube, of course, also owned by Google, is a good resource with lots of tutorials. So this is the first thing that you ever do really with Google Earth Engine is call the data set. So here they have a data set of global forest change from 2015. Then we're running on time, so with these. So this data set is actually, it's not satellite image, it's a vector file where you have a data set that shows regions with forest change in terms of forest lost, forest gained. And here, for example, we have all of these different bands here. So if we wanted to look, go into this data. So here we're looking at the GFC 2014. So here we're looking at the tree cover 2000 band. You can call any of these in the same way.
Amazing.
And you can change your, well anyways, the point here is, it's not just about the visualizations, but also being able to do calculations. So if you're interested in this tutorial, the next part talks about quantifying these pixels. And then there's different libraries you can call which translate the pixel value based into an area, because obviously different satellite images might have a different pixel resolution. So if you're interested in this, it's very easy to do. The last thing I wanted to show you was one of my favorite calculations. It's called the greenest pixel. So it's really great over places that have significant cloud cover, like Papua New Guinea. This is, I know coffee growing countries have a lot of cloud cover usually, and so a lot of the satellite imagery has almost consistent cloud cover. But what you can do, and what I did in this code, is based on NDVI, you calculate for each individual pixel which pixel over a time series has the highest NDVI value. So that's essentially the greenest pixel, and then you can make an image composite of dozens of satellite imageries so that you have what is a map without cloud cover, which is pretty great. So here, this is the NDVI of a single image. So it computes the NDVI using band 8, which is the new infrared, and band 4 red. Displays the result. And then based on the NDVI, it builds a mosaic of the greenest pixels. So you take something that looks like this with all this cloud cover, and with a few more images, you build something that looks very crisp. And the images used to build this cloudless composite are based on these filter dates from Landsat 8. So it's from May to August of 2017. So I think that concludes my talk. I was going to go through this tutorial, but I think it's probably something that is, well, it's not satellite imagery, so it's not really that interesting. So, any questions? Yeah?
Is this free?
Oh yeah, it's all free. Yeah, that's the best part about Google Earth Engine is, so this is made from Landsat 8. So Landsat 8, that was the US mission with NASA as a US satellite at 30-meter resolution. So 9 bands at 30-meter resolution. These are the wavelengths. So for here, you would use band 4 and band 5 to calculate near infrared. So yeah, the two main satellite image collectors for Google Earth Engine are this Landsat 8 and Sentinel 2. Google Earth Engine is also free, which is pretty amazing. Obviously, the interface, the coding is in JavaScript. You need to request access, but as students, I'm sure that they would sign you up. I've already signed up, so. And there's all the data sets that I showed you at the start of the talk too, so you can access. There's so much here. Some of them are country specific, like Canada annual crop inventory. We have digital elevation models in Australia. There's some that are global as well. Here's a global DEM. Population density. So you can look at like population density versus drought regions. You could look at drought, for example, with NDVI to see annual change in NDVI, and cross that with population density and look to see regions that are perhaps at threat of famine or low crop production. More world population. Here's the Sentinel-2 missions, multispectral. We have weather data, near real-time carbon monoxide. That's cool. I haven't seen that one.
So is Google Earth Engine lifetime access?
Lifetime access?
It's like once you apply for it, do we give you access forever, or after 5 years they take it back?
I think it's. No, they haven't kicked me off the platform yet. I think it's pretty much forever yet. But the reason it's by request now is it's actually still kind of in the experimental phase. So Google Earth Engine has really only been around for about 2 or 3 years. So it's right now it's really just for research purposes. Yeah, it's extremely powerful. I mean, imagine having to do the same kind of analytics with something like Grass or an Esri product. Now, if you just have your code in JavaScript here, every time there's a new satellite image released, which is about every week, you just change your dates to the most up-to-date image and run the same process. And that's the only thing you really need to change. And it takes maybe like 4 or 5 days for a satellite to get up onto their system. So, today is October 3rd, so probably the most recent image you could look at is maybe about 5 days ago.
The green strip, the code, is it written by you, or is it like, does the Google Earth Engine is it?
The green strip?
Like the one you are showing now?
The comment here in the code or the screen script?
Like the whole script.
Oh yeah, this is the entire Google Earth Engine interface.
Wait, so as in this is written by you?
The code, yeah, is written by me.
Okay.
Yeah.
So I was wondering whether you do it like you look for places that has the best coffee view. So like you look at elevation data, then you combine it with like precipitation and
Yeah.
things like that. Do you do that?
I'd like to do that more, but that's definitely a use case for it. And also to like weather data, you can look at a lot of specific weather data, or you can look at recommended areas for new coffee production by looking at, for example, terrain slope. So coffee has a very specific ideal terrain slope of about 15%. Volcanic soil is ideal for coffee, so you can kind of mark areas. Papua New Guinea has a lot of volcanoes. You can mark those areas and then kind of do a buffer zone around those volcanoes, north versus south facing slope. So yeah, there's a lot of factors.
What techniques do they use for mapping out the terrain?
Mapping terrain?
Yes.
Those are more with, that's really LiDAR in order to get digital elevation models. So that's different than satellite imagery. So LiDAR is more a satellite sends out kind of a laser that bounces back to the satellite, and based on the time it takes to get back to the satellite, it determines the distance and the relative elevation. So there was the set, where where I had the different here we go. So yeah, that would be all DEM. And see, like this is Amsterdam in the Netherlands, I would assume. So you even get the elevation of the individual buildings. I guess this looks like the train station. So yeah, that's very high definition elevation model. So here's another DEM in Australia. So yeah.
Is the NDVI data from different kinds of soil actually different? Do they each have different indices?
Of NDVI?
Yeah, of like different kinds of soil, like volcanic, like red soil.
Yeah, I mean there would be some consistency between volcanic soil across based on like what the composite is, but in terms of spectral signature too, each type of soil would have a unique spectral signature. But it could vary, obviously, based on how wet the soil is, how much vegetative growth there is on top of that soil.
Just following up on the previous question. I was wondering if you do use the LiDAR data to correct for the area that you've mapped out? Like if there's a slope or not?
No, not for me, because it's the area where they dry the coffee is just like a flat area.
Okay.
So there's no need to.
Like what about the farms? Let's say they're growing at a slope, like farming on the mountains. So there must be like an area component that you're taking.
I don't even actually look at area under cultivation because the coffee farms are obscured by the forest. You can't even delimitate where the coffee farm starts and stops. But I would, for example, I do use digital elevation model for looking at something like waterlogging in the soil. So looking at watersheds, you don't want waterlogged soil with coffee because the roots will just kind of will just destroy the roots. So that's a risk factor that you look at with digital elevation model. So yeah.
Do you have any findings that you came across about Singapore?
Oh, about Singapore? With NDVI in Singapore? Well, we could look at. Not so much. There's a lot of land reclamation going on around Changi Airport, which has been interesting to follow. In terms of looking at the forest data. This is a good visual of forest loss and forest. looks like a lot of trees are growing out by Changi Airport. Because blue is forest growth, and whereas red is forest loss.
Green city.
Yeah.
Like how far back can you access the data?
Sentinel-2 goes back about 3 years, Landsat is about 6 years. A big difference in the spatial resolution, which is why I prefer using Sentinel-2.
So when you used the code just now, did you like get data from the difference from 2015 till now? And then did you?
Yeah, so that code is within the data set that you call. So that's not satellite imagery, that's more of a raster file where for every single point there's like forest, no forest, so it could be binary data. And so from there you just take a look at forested areas in 2000 versus 2015, and then calculate where is there forest in 2015 that there wasn't in 2000, so that's forest gain, forest loss.
Where do you get the data from? Like, do you have to know specifically a length? You want like forest, you need to go Landsat?
No, for forest, so there's all data sets. So there was the page I was showing you with like dozens and dozens of data sets. So Sentinel-2 and Landsat are just two of the data sets available. And those are two that I mainly work with. But there's data sets for population density, weather data sets, methane gas release data sets, global ocean temperature data sets. So lots of different data sets. And so you can really play around with all of them.
So these data sets are first analyzed by some other agency and then uploaded, and then you can use that to like kind of.
They're pretty raw. They're corrected sometimes. Like with the satellite imagery, there's atmospheric correction that goes into the process before it's on Google Earth Engine, so you don't have to do that process yourself.
Something like this exists for not Earth, like for other like the moon. Oh wait, I think
yeah.
Or like is it? I don't know. Is it the same thing?
There's no satellites though going around the moon yet. So
Not yet.
maybe one day. There's not much coffee going on the moon.
Oh yeah.
Not yet.
Oh yeah.
Right. Yeah.
Could I ask about the technique that you developed specifically for coffee? What's the innovation, if you don't mind sharing?
Yeah. Just to elaborate more on it, or?
Up to you. How much you want to talk about?
Yeah, it's just doing a classification of sun drying coffee basins to see, look at pixels where there's coffee versus no coffee, and then maybe a drying basin is 50% full versus same time last year was 100% full. So then you know that this particular coffee farm would have 2 times the production it did last year, and with enough coffee drying basins in your sample, you can derive national coffee harvest, which is what I primarily look at. So.
How would you approach this data with as to like who would you go to and be like, okay, so like who would you help and who would you not help with this data? That was the question.
Yeah, help with predicting kind of coffee production, so or even verifying coffee production, because there's a lot of countries that lie. Manipulate data. In the coffee markets, I'm talking specifically about Brazil, because they already produce about 50% of the world's global coffee supply. So if the Brazilian Coffee Board says, oh, we're not, they underestimate how much coffee they're actually producing to drive coffee prices on the commodity markets up. With this kind of imagery, you can say, okay, well, you say that you've only produced this much coffee, but I see that you're actually drying this much coffee. So,
Like, who would you give this data to? Like, for example, if this Brazil is like, I don't know, to use the word lying, then who would you go to and like give this data to? Like,
other kind of coffee. There's the International Coffee Organization that tries to kind of reduce variability in coffee prices, so coffee farmers can have a more predictable income. Or you would think commodity traders, but with commodity traders, they spend so much money actually on the ground researching coffee production that my analysis is a little bit retrospective to what they're able to determine. So it's more kind of for other kind of coffee research institutions like the Coffee Board of India, which I was working with them in India when I came up with the method of using satellite imagery for drawing basins, and that's a very reputable coffee institute. So I backtest a lot of my findings with what they're producing. That's my result. Yeah.
Just wondering, like, what are the future plans for your company?
Yeah, I'd like to move more into geospatial analytics and kind of general satellite imagery consultancy, and capturing aerial imagery as well with drone imagery, and kind of doing orthomosaics for kind of calculating things like vegetative biomass, or looking at even flying drones that have near infrared cameras on them to detect more high definition. What kind of areas of your farm are low on NDVI values, so you can address those areas of the farm. So I'm also currently working for World Coffee Research and helping them manage a lot of their kind of geospatial data sets. So pretty busy at the moment, but I am looking for anyone who's interested in maybe helping. Yeah. My email address, if you want to write it down, is peter@greeneye.co. And my website is obviously greeneye.co. So, yeah. I'm looking to expand just kind of general satellite and geospatial analytics outside of coffee, because the coffee market is very competitive. So actually, when I first came up with this method, I was very secretive about it and wouldn't share it with anyone. But now that I've realized how much competition there is in the market and how actual little value my method has for commodity traders, it's more geared towards that. It's kind of like helping assess kind of global coffee productions as a verification method, and it's not really something that's going to make you millions of dollars by fronting the markets. So if you think that is what I can do, that's not the case, because Olam has dozens of people right now as we speak, probably trudging through the coffee farms in Sumatra, looking at the beans and the bean size and the flowering. So there's a lot that goes on in predicting coffee prices long before the harvest even comes around. So, but I was talking also other really impressive innovations of using satellite imagery. There's people that are using high definition imagery to count cars in parking lots outside certain stores, like for example, as an indicator of economic activity. How many cars are parked outside Walmarts in the United States? See how many people are buying stuff. One of the most fascinating things I've heard of is people using, again, high resolution satellite imagery to look at these cylinder oil reserves that they have in Saudi Arabia, and based on what time of day the satellite image was taken. So you have your sun position in the sky, and then based on the shadow reflected off of the sides in Pythagoras theory, you can see the shadow reflected on the oil and calculate the depth of these oil tankers, so you know how much oil is in reserve on these oil tankers. And yeah, so that's really, really advanced spying techniques to know how much oil is coming out of Saudi Arabia. I'm really interested in more kind of ocean applications, but for a lot of these satellite missions, the satellites only really capture terrestrial imagery, obviously because the Earth is 70% water, and for most people that would be a big waste of resources. It's just capturing fluid imagery. So.
Ocean imagery, like oil offshore, onshore oil gas reserves downstairs, down in the ocean. Is that what you're interested in?
More looking at things like plankton blooms or coral bleaching to see kind of global reef degradation. Looking to see changes in ocean temperature to see perhaps reef systems that are at risk of coral bleaching. This is something that I'd like to look more at with kind of probably drones because of the high resolution nature of actual drones compared to satellites. Yeah.
To what extent is satellite imagery analysis reliable as compared to like field work?
Yeah, you definitely need field work to kind of verify the findings that you're getting with the satellite imagery, and to, excuse me, I guess help define your pixel. So, you know, this imagery that's coming in at 10 meters squared, you could go out into the field and, you know, find at the exact point where that pixel, the corners of that pixel, and then you could experiment by like laying different materials across that 10-meter pixel and see what the spectral signature is from Sentinel-2 for those materials. So, you know, if you wanted to like classify areas that are like growing mangroves or something, you could go out and find 10 meters of mangroves and, you know, see what, you know, cross-reference that with the satellite imagery. So that's why it's so exciting, is because it's real world and then also the computer world. So, yeah.
I actually asked my prof about the like estimating cloud cover using satellite, but he said there's a lot of problems with like just water reflectance and things like that. So I don't know, do you have any solution out of that?
For cloud cover?
No. So water, like if you want to estimate like coral bleaching or coral cover.
Yeah.
Yeah, but my prof say water is a big problem because
Yeah. Yeah, well, so there's definitely like a certain depth where satellite imaging will help you. Probably anything past like 5 meters. But you can look at things like, I don't know, maybe plankton blooms on the water surface might have a very, very minimal effect on NDVI. So there's definitely a lot still to look at. Any other questions? So many questions. Yeah. Any questions from the very back?
One question. Yeah. Where can we get the best coffee in Singapore?
Oh, maybe, I don't know, Delaware Coffee. I go there just because it's across the street from the library. Yeah, and they have Sweet Little Rain. Have you ever had their Sweet Little Rain? It's a wad of cotton candy over the coffee, and the steam from the coffee melts the cotton candy, and the cotton candy rains into your cup of coffee. it's very over the top. So it's also $10, so I've only had once.
Any other final questions?
Yeah. Check out my website. If you're interested, sign up for Google Earth Engine and email me, and I can maybe send you some of the code just for looking at NDVI or the greenest pixel code. Or obviously the tutorials are really easy to get to as well.
Great. Yeah. Thank you.
Thank you very much.